So quick background on Revinate. Revinate is a hospitality data company. Our customers are hotels. We have tens of thousands of them spread across the globe. Our job is to write software to help these hotels generate more revenue. We do that by making offers pre-stay, targeted offers, pre-stay, mid-stay, and post-stay via email, messaging, and voice channels. Now, we're not going to talk about the activation channels today. Instead, we're going to focus on the back end, the data pipeline, because the data is critical to everything we do. So a quick plug for my employer. Slightly biased, but Revinate's an amazing company. We've won several awards, and we've actually generated tens of billions of dollars for our customers. So it's a very sticky product. Our customers love us. Want to talk about our journey with Kafka. So let's rewind back to 2018. At the time, we had one, maybe two teams using Kafka on a limited basis. Our backend was a monolith that processed all of the data that we received from customers. Over the last 6 years, though, we've invested heavily. We were able to decompose that monolith into a microservices architecture. We went all in on Kafka. We're now big fans of Kafka Streams. We're now at the point where we have, I could say, over 40 Dockerized Java microservices running in Kubernetes. Each one has a specific responsibility, and practically everything is powered by Kafka. We've learned a lot of lessons over the years, and that's really where this talk came from. We're hoping to share what we learned to benefit others. So it's important to talk about our domain. Dean and I are going to present some problems that we encountered and the solutions we came up with, but it was all within the context of our specific problems in our domain. Had we encountered other circumstances, we may have chosen different solutions. And so something to keep in mind as you see what we're presenting, please keep in mind your own situation, your circumstances. You may end up actually on different solutions than what we came up with. But we're in the hospitality space. The data we work with is hospitality focused, so everyone here, I assume, has been to a hotel before, stayed at one. Room reservations, hotels also have restaurants, spa, golf courses, so we deal with those types of reservations as well. Lots of guest data in the form of the profiles, preferences, and so forth. We actually see this full life cycle. So when a guest makes a booking, we'll receive that as an event. When they check in, we get another event, and so on and so forth, all throughout the life cycle of the stay. Something I want to stress, and we'll come back to this throughout the talk, is these source systems that we receive data from, at least most of our data, they're owned by the customer. And so we really have no control. There's actually this, the hospitality space is kind of fascinating. Neither of us were in this before we joined Revinate. But the systems, some of them are modern, cutting edge, cloud-based, using APIs. Others are on DOS, like literally DOS. And then there's a whole suite of in between. And so our job is, at least at the very topmost or kind of leftmost side of our pipeline, is to be able to connect these systems. And so we have to support a variety of different integration methods, such as webhooks, APIs, FTP, email. Some of the data comes to us in batch. Our pipeline is built for real time, but we have to support batch inputs. And you'll see kind of some of the implications of that as we go. We have at least once semantics. And then our messages are atomic, which is great. But the schemas can actually be kind of complex because they have this nested architecture of, or the structure of, you have a reservation, which can have a profile inside. Profiles can then have specific pieces nested within there. So we'll get into that in a little bit. And then lastly, when it comes to order, order is important, but it's not always reliable. These customer systems, when they're sending us data, we're kind of at the mercy of them. This is this constraint that they've put on us. It's like, oh, here's our data, deal with it. And that's what we've had to do. We've had to deal with it. So the first problem we want to dig into is supporting diverse message types. I'll pause for a second and just point out this graphic at the bottom. This is a simplified view of our pipeline. I mentioned a little bit earlier, we've got these clip arts on the left. Those are hotels. We got to be able to connect to these systems over a variety of different formats or connection methods, whether it's FTP, email, API. We get the data in a variety of different formats, whether it's JSON, XML, CSV, so we've got to transform the data. We then need to split it, especially if it's coming from a batch job, where let's say it runs every 10 minutes, every 15 minutes. It could be a giant payload that has hundreds or thousands of reservations in their reservation events that we then need to split up. We do some deduplication, and ultimately we sync it to a database. So we'll revisit this graphic as we go through the presentation. But this first part, we're going to talk about kind of the middle of the tail piece of the pipeline, where we handle messages basically after we've put it into protobuf. How do we actually support these different types?
All right. Hey, everybody. So I reckon all of us have seen or read some variation of the quote I put at the top here. The core idea is that you put all message types that are the same into the same topic, and that each Kafka topic contains just one message type. And that's pretty much what we started with. We'd put a room reservation message into a room reservation topic, a restaurant reservation into a restaurant reservation topic, et cetera. And I think the logic here is fairly sound. It's sort of strong typing for Kafka topics. You might prevent some errors if you aren't putting random messages into the topic. You reduce the runtime challenge of having to figure out what the message is, if it is always the same type coming out of the topic. But as we expanded our schema, we had a more complex schema. We ran into some things that were a little bit more challenging. So the first problem was that if we have the room reservations in the room reservation topic and spa reservations in a spa reservation topic, it makes it a challenge to enforce any kind of message ordering across these types. So for example, if message B down here, spa reservation, can only be processed after the room reservation A, it's a little bit challenging to do that when these things are in different topics. Another kind of problem is that there are variations on messages. So here we have a room reservation. We have a room reservation updated event that has a lot of fields in it. It has a reservation ID, it has account information, name information, it has a check-in date, a checkout date. On the left side, with the room reservation deleted event, it only has the reservation ID. So, I mean, you can make the case that the room reservation deleted is really just an updated event with a bunch of empty fields. But the truth is they are different types. They're processed differently, and we want to keep track of them differently. The schema itself tracks them differently. And it's important here that we also order these in the correct order. You can't really do a delete until you've created the room reservation. Another sort of problem that we run into, and Daniel alluded to this a little bit, is that we have room reservations and golf reservations that can contain profiles. So the profile is a description of the person who made the reservation or one of the people who's staying in the room. It's important to note here also that the profile message stands by itself. It's a valid message all by itself. So how do you handle room reservations in the room reservation topic if they contain profiles? Do you put those profiles into the profile topic? A little confusing. So another situation is where you have a service that's consuming from topics A, B, and C with message types A, B, and C, and you need to add a new message type. So here at the bottom with schema up, this guy, up, back, there. If we add a new schema M, we'd have to create a new topic M, and then we'd have to add that topic to the service. It's not clear that this is necessarily a problem. That may be fine. But we have services that don't necessarily care about the message type. So it's possible that the service could process this new schema message M without any code changes whatsoever. But in this model, we'd have to add the new topic, and we'd have to go change the service in order to do that. So our goal was to create a schema where we can add new message types without necessarily having to create new topics. We want to be able to enforce ordering across the message types. We'd like to be able to ensure that every component inside of the message is processed consistently, irregardless of the type of message that it's in. And then finally, this is more of a developer thing, but on that previous slide where I showed you the service with lots of inputs and lots of outputs, if you have different message types all over the place and you have different SERDES, different serializers and deserializers for those, it's kind of a mess, kind of a hassle to maintain.
So the solution we landed on was to use a generalized schema that can be used for all topics. And so we're big into protobuf, and actually this predates the schema registry's support for protobuf. I know it does today, but so within our protobuf schema, we basically have the notion of a hotel event, and it's represented here in this graphic, that's kind of the parent of everything. And so within protobuf, you can have a one of type. And so within that, we have a guest golf reservation, room reservation, restaurant reservation. And so you can specify exactly what you want to have your type be. It's like, oh, this is going to be a room reservation. Oh, this will be a restaurant reservation. But everything is a hotel type. And that actually makes it really easy to write to any message, or excuse me, any topic, because they're all just hotel events. It doesn't matter if it's this topic, that topic. They're all hotel events, and you can deserialize it and figure out exactly what it is based off of the one of. I'll also make a plug for the Buff CLI. Some of you may be familiar with that. Been very helpful for linting, formatting, catching breaking errors. So if you're using protobuf, really heavily recommend the Buff CLI. One disadvantage to call out, when you use one-ofs, your code ends up looking something like this, proportional to how many different options you have in the one-of. You basically have to go and say, okay, I'm going to have this switch statement. I'm going to figure out what the event type is of the hotel event. Okay, great, it's a room reservation. Let me go to the next level. What's the event type within the room reservation? Is it an update event? Is it a deleted event? And so forth. So just something to keep an eye on. So the next problem we wanted to talk about was handling large messages. I mentioned a little bit earlier, we're basically at the mercy of these hotel systems when they send us data. Some of them, they'll upload messages to FTP, and it's these batch jobs and big, giant messages. And so this section talks about how do we handle these big messages. I'll call out the Kafka limit. I'm sure most people are familiar with the 1 megabyte. At least that's the default. You can configure that and change that if you want. But that's an important milestone or marker, if you will, when you're looking at your messages. So for us, nearly every message is under 1 megabyte. In fact, and this is a sample of just 15 million messages we got, practically everything, 98.8% are under a megabyte, and almost everything's under 100 kilobytes. And so it's relatively small messages, which are great. The downside, though, is we also have other messages that are not smaller than 1 megabyte. And so you can see here, and we had to, there's a long tail, and so we had to break this up into multiple slides so it all fits. But you see the y-axis changes here. Instead of dealing with millions, now we're in the tens of thousands. So we got 1.2% of our messages are between 1 megabyte and 10 megabytes. And then we also, this long tail where we have a even smaller, the y-axis is now, it's at 9. We have this long tail of messages, large messages. So in here, I think we go up to 400 megabytes, but we've seen in production, our production system, messages as large as 750 megabytes. So imagine here coming through your pipeline, and we have a real-time streaming pipeline. Here comes a 750 megabyte message. What do you do? So that's the problem that we faced, and this is how we addressed it.
Yeah, so to solve the problem, we riffed off of the claim check pattern. And over here on the left side of the screen, you see the producer service. He's about to send message M1 out to Kafka. He's all set to go. But before he does that, he's going to take a look to see what the size is of that message and see if it's under a megabyte, if it's under the max message bytes. If it is under that limit, then he can send that message with the message payload in the Kafka message straight out to Kafka. If it's greater than a megabyte, then he's going to have to first take the payload out of the Kafka message, put that payload into S3, and replace the payload in the Kafka message with a reference to the S3 object that he just created. And then he can send that to Kafka. Over on the right side of the screen, the consumer now is going to receive the message and check to see if it has the S3 reference. If it doesn't have an S3 reference, the payload is in that Kafka message, he can process it. Otherwise, he has to go out to S3 and fetch that payload before he can do the processing. Some things to think about here when you're doing this is that compression, for example, is going to affect the message size. So 3 or 4 megabyte message uncompressed may compress down to less than a megabyte. So you need to think about that when you're measuring the size of the message. We did change the message schema. We added that S3 reference. In fact, we replaced the payload, the entire payload, with an S3 reference. Another thing you need to consider is how long will these references, these payloads in S3, how long are they going to live there? If you've got a Kafka topic with infinite retention, then you might want to leave them in S3 forever. If you have something other than infinite retention, then you might want to think about how you're going to get them out of S3. There are alternative ways to do this. In particular, I can talk a little bit about the LI Kafka, the LinkedIn Kafka library, which does the same thing with large messages. This library has a custom producer and a custom consumer. If you send a 10 megabyte message to the producer, it will break that 10 megabytes into 10 segments and send each of those segments as an individual Kafka message. On the consumer side then, their custom consumer will reassemble those into one message before it's deserialized and returned to you. It will also track the acknowledgements. It'll make sure that it doesn't acknowledge any of those segments until they've all been assembled.
All right, so I want to talk about deduplicating messages. I mentioned a little bit earlier our 750 megabyte giant payload. We can't do the deduplication at the early part of the pipeline because this payload could have lots of reservations in there. It's not until after we split and we say, okay, maybe the 750 megabyte payload has 100 reservations. Great, here's one reservation, here's another. Turns out that these two are the same or it matches one that we saw previously. So we're going to dig into deduplication, what happens right after we do the split. Some context, actually I think I provided most of this already. Really the cause of this is third parties. So it's our customers. Our customers are doing this to us. They're sending us their data in a format or a structure which is really beyond our control. And so we just have to deal with it. We have to figure out how do we handle the deduplication. And it's important because we don't necessarily want to waste resources. We don't want to reprocess something that we've already processed again. And so our goal is to be able to identify duplicates so that we can handle it accordingly. Maybe it's throw it away, maybe it's just log it. Whatever it is, we first need to identify, yep, this message that we have right here, this is a duplicate message, we've seen it before.
So before we can duplicate messages or deduplicate messages, we need to figure out what makes messages duplicates. So I have two messages here. The first field, the received field in both of the message, is a timestamp. Revinate added that field when we received the message. So that particular field is always going to be different for any two messages that we look at. So before we can duplicate or deduplicate messages, we're going to have to remove that field. So the steps here, when you receive a message, you're going to need to remove any fields that aren't useful when you're building your deduplication equality function, whatever that looks like. So you're going to remove those fields, and then you're going to hash that value and put it into a dedupe table so that we can compare it to other incoming messages. So the final process now looks like this. For every message that we receive, and I went there, sorry. For every message we receive, every message X, we're going to have to remove those fields. We're going to have to hash that value. Then we're going to join that hash value of the incoming message against all of the hashes stored in the dedupe table, every message that we've already received. If there is a match, it means that this is a duplicate. And that means that we can discard the message, we can log the message, we can do whatever we want to do with the duplicate message. If there is no match, then it means it's a new message. It's not a duplicate. We can go ahead and process the message. Did I do that? We can process the message and send it to outbound. But in addition to processing the messages, we now need to send that hash value to the duplicate table. So we're going to send the hash table out to a deduplication topic so that it'll get into the dedupe table. We think about what the structure is of the dedupe table. It makes sense to use the hash value as the key for that entry in the table. We're going to be doing a join on it. The value could be really anything you want. We're not really merging. We're really just checking for existence in the table. We're going to use the current timestamp. So when we create a new entry in that table, we're going to put the hash value as the key, and we're going to put the current timestamp as the value. And the reason for that is that we want to be able to clean this table up. If we don't clean this dedupe table up, it's just going to grow forever. And as Daniel pointed out, what we usually see is that a message will arrive at midnight, and then we'll see a duplicate of that at 1 o'clock, at 2 o'clock, 3 o'clock, up until midnight again. And then we won't see it again. So to implement a time to live function on the dedupe table, we built a punctuator function that fires every few minutes. It scans the dedupe table, looking for any message that's more than 24 hours old, and it issues a delete message to the duplication topic. If your duplicates are likely to have the same key, if you're generating the key from the values inside of the message, for example, and they have the same key, then you'll probably use a k-table for your duplication table. Otherwise, if you're using random keys or no keys at all, then you could use a global k-table or you could rekey them. Things to think about.
All right, so I want to talk about message prioritization. This applies really throughout the whole pipeline. Something to call out is that prioritization is effectively it's a business need. It's a business requirement. It's like, oh, this message or set of messages is higher priority than this other set. That's different, of course, than Kafka's ordering. That's a technical construct. It basically says within a partition, if you put these messages there, that's the order. So priority and order, they don't always sync up. And so the problem we're trying to solve for is if a topic contains messages where the processing priority isn't reflected based off of the partition order or the timestamp. So a couple examples here. Let's say you have high priority message E. It's higher priority than A, B, C, D, but it is published after the fact. And so I actually want to give priority to E, but it's after these ones that have come first. Similarly, on the bottom graphic here, what if we have a glut of low priority messages? We've said that, oh, well, we just know that V, W, X, and Y are low priority. We don't need to process these quickly. It can take a little bit of time. But there's a bunch of them, and so actually they're kind of clogging up the pipe, so to speak, and preventing us from then processing a regular message, such as Z here. So how do we handle that?
All right, so the first thing that we need to do is we have to make sure that our producer can spot priority messages. We said that message order and priority are actually different. Message order is what it is. Priority is something above and beyond. Once the producer actually sees that it's priority, we need some way to ensure that that high priority message is executed as soon as it possibly can be, and that the low priority messages aren't going to block anybody if we can avoid it. There's a couple of steps here. We're going to actually sort the high and low priority messages into their own topics, and then we're going to look and see what we can do with that. So the first step is to sort them into different topics. So the producer before was producing messages A, B, C, D, E in message order. E is a high priority message, but there really wasn't anything the producer could do about it. But now we've added a high priority topic so the producer can put E into the high priority topic. Similarly, at the bottom, the producer is able to put the low priority messages into a low priority topic. So what does that get us? So on the left side now, we have the normal high and low priority topics, and we've successfully sorted the messages into those topics. We take a look at what the consumer is going to do now, and we've only got one partition here, just to make it simple. So the consumer is going to try to build a batch from all of these messages. It's going to use a round-robin partition algorithm to retrieve these. So if the message batch size is sufficiently large, then he'll start with, say, the normal topic at the top, and he'll start filling the batch with A, B, C, D, Z. If he still has room, he'll throw in E. If he has room, he'll throw in V, W, X, and Y. But then he'll look at this batch, the consumer will look at the batch, and Streams will process the messages using stream time, using the message time, I should say, which means that he's still going to process A, B, C, D before E. And he's still going to process V, W, X, and Y before Z. Okay? So we didn't really get anything by doing this. Conversely, if we make the batch size really small, like one message, so now on the first polling event, he'll go and he'll grab message A and process it. On the next polling event, he'll grab E, process that. It seems better, but it's completely dependent on the configuration, how many messages are in how many messages are actually in that topic at the time. So it's not ideal. If we add more partitions, we have the potential to improve our throughput. We have an extra task now running, but we still have this round-robin consumption, and we still are processing by message time. So we really haven't done anything at all. So this is kind of magical to me. If the actual the process that you're executing does not have any aggregations in it across these topics. On the left side, we have exactly what we had before, but now streams will build these subtopologies for us. So the first thing to notice is that there are a lot more tasks. So we have the potential to do a lot more parallelization here. Okay, so we get much greater throughput. But more to the point in terms of prioritization, note that now nothing is blocked. None of these topics are blocked by any of the other topics. So the high priority messages are going to execute as soon as they possibly can. Not necessarily before A, B, and C, but certainly as soon as they can be processed.
All right, so I want to talk about broadcasting events. I mentioned a little bit earlier when we were dealing with FTP, we have some customers that are on systems that they send us their data via FTP. We have other customers who are on systems that'll publish messages to us. So think of it like a HTTPS post. This is how we address those, or rather, this is some of the problems we see. And so the first thing that jumps out is a post is effectively, it's synchronous. You send a message as a client and you expect to receive a response. It's synchronous. Whereas our Kafka pipeline, it's inherently asynchronous. We've got services with Kafka topics in between, so it's an asynchronous flow. And so that's one challenge that we've had to encounter. The second piece of that is, now let's say you have more than one service running. Typically you do in production because you don't want to have a bad day. And so we've got replicas that are running. And so let's say that one client connects to service A and sends a message there. It's expecting a response. Great, so the message on our end, it goes from service A, goes through the topics, comes back around to this response topic. Now imagine if that web service A is consuming from, let's just say, partition 1, but that response actually ends up in partition 0, which is being consumed by web service B. Well, now I can't respond to my client because I don't actually have a response to give them. And so these are two of the problems that we've encountered, or that we had to deal with when we were being able to address synchronous requests from customers.
All right, so our goal here is we've got some responses in the response topic, and we want to make sure that the response for the HTTP request gets routed back to the web service instance that received the request. So that's what we have to be able to do. So the way we did this is we introduced Redis. So notice at the bottom of the screen, I did it again. There, all right, here. This pipeline is identical to what it was before. You have an HTTP client, web service, and a Kafka pipeline. So now the web service, though, is divided into multiple threads. So one thread is going to receive the HTTP request, just as it did before. But now it's going to enter into this table, a local table on this particular instance. It's going to enter with the key, the request ID, and it's going to create a completable future for the response. Once it's created that entry in the table, it can post the message to Kafka. Then it can come back and block on this future. Meanwhile, the request goes through the pipeline, and eventually we generate a response and put it in here. We've introduced a new completion service whose only job is to read all the responses and to publish them into a Redis channel. Coming back to the web service now, we have another thread, which is a Redis thread that subscribes to that Redis channel. So now it is going to see every response that was published into that topic. For each response that it sees, it's going to look up to see if the request ID is in its table. And if it is, it'll go ahead and complete that future. By completing the future, he's unblocking the HTTP thread who was blocked on that future. And so now that thread, the HTTP thread, can access the response from the future and return it to the client.
All right, so then the last topic we wanted to cover is parallelization. Of course, parallelization is kind of inherent in Kafka. You've got partitions. But this we wanted to talk about, how do you parallelize beyond the partitions? And so this is especially important within our transformation layer, shown here, when we can have some of these large messages and maybe they take a little bit longer to process than others. How can we parallelize them? And so one thing to call out first is the difference between latency and throughput. Latency, of course, is having to do with delays. Throughput is really volume. It's how many messages per second can you process. In our case, if we're processing a giant payload, maybe let's go back to that 750 megabyte message I was referring to earlier, that's going to take some time because we're going to have to transform, I think that one in particular comes across as like XML. We have to transform that into our internal canonical format. And so transforming that it's going to take some time. We don't want that one message that's at the front of that or at the current latest offset that we're processing to then delay the processing of every single other message that's behind that message on that same partition. And even if you were to increase, maybe I'm stealing what you're going to say, increase your number of partitions, that doesn't really help because you're still behind that same stuck message. And so we refer to that as a stuck partition, which Dean will actually dig into a little bit more here.
Yeah, so we call this a stuck partition. I've seen it called a slow consumer. We call it a stuck partition. I'll show you what we mean. So at the top, we have a consumer. It's been assigned partition 0. At time 0, the consumer begins processing message 35, the message at offset 35. At time 2, we hit a polling timeout. It took a long time. So that triggers a rebalance. At time 4, a consumer is going to resume or start processing message 35 again because it was never acknowledged. Again, at time 6, we hit a timeout, which triggers a rebalance. Another consumer starts, and so on and so forth. So what the net result of this is obviously that 35 is never acknowledged. Messages at 36 and 37 are never processed. Anything at 38, 39, they're all stuck. They're not going anywhere. I can also point out here that this polling timeout, we've seen it be like a Java OOM, an out-of-memory exception. It can happen as well and cause kind of the same problem, cause the pod to go down, and you get the same problem. So our goal here is to prevent these stuck partitions. We've got to avoid this. And generally, we'd like to improve message throughput if we can. We'd like to do that without increasing the number of partitions. And we don't want to dive into latency. We don't want to go figure out like why these messages are slow. We're just going to take it for what it is. All messages are going to be processed. Message scheduling order is going to be preserved. Message processing order is not guaranteed. I have no idea what that means. Let me show you what that means. So we have a consumer, and he's consuming messages from, every time, from partition 0 and 1. He's assembled a batch of messages from those two partitions, and I labeled the batch with P02, P03, which is the partition and the offset. So similarly, P124, P125. When the consumer sees this batch, it's going to sort these messages in the batch into queues. And there's one queue for each partition that this consumer has been assigned. He's going to assemble them in the queue in the partition order. So he's going to assemble P1, and then P2, then P3, P4. Okay, that's going to preserve scheduling order. That's what I meant. Now, on the far right, we've got the thread pool over here executing the messages from the queue. So they begin their execution in the correct order, maybe, yeah. But there's no guarantee, obviously, with these threads that they'll complete their processing in that order. So for example, it's entirely possible that thread 3 completes before threads 1 and 2. And if it does, and it sends its message out, it sends a result message out to Kafka, they're not in the order that they originally came in anymore. What's important to note here is that if thread 3 does complete before threads 1 and 2, the consumer will not acknowledge the P3 message until P1 and P2 have been acknowledged. And that's important because if we complete thread 3 and the consumer goes down, when we come back again, we will not have acknowledged any of these, and we'll begin with P1 again, okay? So that's good. We won't lose a message. But note in that scenario that message P3 would be executed 2 times. It was executed in the first time, and then it came back and was executed again. So this is a Kafka solution. This is not a Kafka Streams solution. We're dealing with the partition assignments. We're manually acknowledging these offsets. So this is Kafka. If you must use Kafka Streams, this solution won't work for you. I'm going to revisit latency now. If latency is just generally high for all of your messages, this will help you improve throughput because you're running more in parallel. If you have the outlier message that's 3 or 4 standard deviations away from the mean, and that's causing a stuck partition, for example, this can help prevent that as well in 2 ways. One, that stuck message is going to be running in its own thread. There are other threads processing other messages. That said, you won't actually advance past it because you're not going to acknowledge anything. But with the threads, you have the ability to kill the thread, to time it out. So you could say, I'll let it run for 10 minutes, and then I'm going to time it out. I'm going to kill that thread. I'm going to acknowledge the message, and I'm going to fail it, whatever you want. You can do whatever you want with it. But you now have that ability. You might want to look to see what is causing your latency issues, your process. If you're doing a lot of CPU computation, so you have just a complex process there. Unless you have a lot of CPUs laying around, you're not necessarily going to gain a lot by throwing more threads at this. If, on the other hand, your latency is caused by third-party services that are slow, and your threads are blocked all the time, then you're probably going to gain something by having more threads. There is a Confluent parallel consumer. We've looked into it. I haven't used it. We did ours independent of that one. And I believe, you could correct me if I'm wrong, but I believe that it will ensure processing order. But it does so by adding additional overhead. There's an additional topic, for example. We didn't need that, so that's why we decided not to do it. KIP 932 queues. This may help us solve this problem. I don't know enough about it to tell you exactly how, but we'll wait and see.
Great. That's our talk.